have a talk prepared, and I hope you'll find it interesting. I want to start, though, with some just general remarks so you know where I'm coming from. And so if I can just skip back a little bit, just want to mention, some of the obvious and the things that really influence where we're coming from. And just to realize that this activity of artificial intelligence research is incredibly ambitious. Really, I think that we're trying to understand intelligence well enough to create beings of greater intelligence than current humans. That's really the goal. And reaching this milestone is going to change lots of things, change our economies and our societies. It will be transformational. But it's also important to realize it's a continuation of trends that are thousands of years old, because we've always tried to create tools, and we've always ended up being changed by our tools. So this is what we do. And the next big step is to understand ourselves. And this is a grand quest, and that's what AI is about. Quintessentially human activity of understanding ourselves, making ourselves work better. Now, my own perspective is that this is going to be good for the world. Obviously, it's going to bring lots of changes, but I think it's going to be really good to the extent that good can be thought about at this level. And secondly, I think the greatest bottleneck is we need new learning algorithms and new meta learning algorithms. We need to think at a very abstract level, and we need to design new algorithms. It's not just about doing better on Atari or doing better on the large language model benchmarks. We have to think about very abstractly. And so in particular, we need methods that learn from experience, and that's what I'm going to talk about today. The greatest impacts are still to come, and if AI is a race, it's not a sprint. It's more like a marathon. There are basic things we need to figure out, and this will take a while. Amazing things are happening all the time, but there are basic things that will happen for a while. The basic things will take time. It'll keep going for at least a decade, could be 2 decades. Okay, so today I'm here to talk about the role of sensorimotor experience in AI. I think this is a foundational, and I've been helped in this by many folks listed here, and I have lots of jobs. I work at the University of Alberta and Keen Technologies. I want you to mention the last one here. The last one, Open Mind Research Institute. This is an institute that I founded a year and a half ago, and the point of it is to support young, actually any age researchers to get research fellows, and we support them by funding their research and on fundamental issues in AI, in particular around what we call the Alberta Plan, which you might want to look that up on the web. You also want to look up openmindresearch.org on the web. Okay, so let's get to it. The increasing role of experience. What is this sensorimotor experience thing? Well, let's just do some examples. Most of them I'm going to talk abstractly, but I'm going to go back and forth between the concrete and the abstract. So this is the concrete of sensorimotor experience. See in the upper left, you see soccer players trying to score goals, trying to understand what's happening in their environment, trying to get around opponents, and all sorts of goals. And there's a constant sensorimotor experience just flowing into their minds, into their brains, and they have to deal with that. And animals have to deal with this too. They have goals, and they have a huge flow of sensorimotor experience coming into their eyes and their ears and the rest of their body, and they have to have particular outcomes. Even people talking to each other trying to control the outcomes. So I think it's good to just get some glimpses of real life experience, because now I'm going to be abstract. Okay, abstractly, we have an agent, intelligent agent interacting with this world is in this picture. And I guess I can point. Yeah, you guys can see my pointer, I'm sure. So the agent and the world interact. We send actions to the world, bits to the world. The world gives us back bits, which are the sensations. And these two things are very important elements of making up experience, the bits going in, the bits going out. This is our ordinary interaction. We're living our life. We're the lion. We are seeing our world passing by, and we are choosing actions which cause us to move forward. So this notion of experience is these two things. Actually, it's three things. It's also the reward. So here's the reward shown as a special wire coming in. It's very narrow and thin because it's just one number, whereas like a sensation would be a whole visual images, and your action would be a whole the forces sent on all your muscles. This is what experience is. So these three things going back and forth, exchanging with the world and the agent. And I want you to note, well, so going through the list here, reinforcement learning obviously involves experience. We have these three things. We have normal life, and we learn from it. Now, classically supervised learning, the most common kind of learning, doesn't involve experience because it learns from a special training data which wouldn't be present during the normal life of the agent. So experience is important because it's always available. And then these last 2 points, I want you to focus on them for a minute. Experience is the agent's only access to the world. This is all that it knows. I sent some bits out, I got some bits back. And it's the meaning of those bits is only by relationship to other experience. The bits don't really mean anything. They are retinal images, they are signals sent to muscles, but the meaning is their effect on each other. I guess I don't give the classic example that my supervisor, Andy Bartow, would always give. He would always do this motion. If you can see my picture, my image, I'm closing my hand. And when you close your hand, it's a motor action, and yet it produces a sensory result. Like you can feel your fingers pushing into your palm when you clench it. This is the simplest example of your learning the relationships between your actions and your sensory bits. So this sensory bits, they don't have any meaning. They're just, maybe they predict other things, or but all that meaning is interrelations between the bits. The one signal that does have meaning is the reward. Reward is defined as something that's good to happen, and you're trying to obtain it. But all the other ones are really abstract. So notice this already, we have this tension between abstraction, our goal, and our understanding of the world is quite abstract, and yet it's reduced to something that's concrete, which are these bits going back and forth between the agent and the environment. So this is the question that I want to phrase for you guys. Will intelligence ultimately be explained in objective terms or experiential terms? So objective terms are things like, oh, this is the state of the world. These are objects in that world. These are people and their places, and they're these sort of intuitively meaningful things about the world. Space, motion, distances, all these things are outside the agent. Or this is some sense concrete and objective. Whereas the things on this side, the sensations, actions, rewards, time steps, these are all things inside the agent. And these are all, experience. These are the three things that make up experience. And then the fourth thing is the time step. We have time step. Experience arrives at particular times. We have that. And all of these are experiential. And all of these are about what's happening outside in the world. We use these to talk to each other. These are the natural ways of talking about the world. These are unnatural ways. They're difficult. They're not intuitive. And yet they are the most concrete. And really, they're what our agents and all intelligent systems have to deal with. They have to deal with the data coming in and out. So here's the question expressed in its general form, trying to do that. And now we'll get into it, and you'll see what this all means. Okay, so I'm going to break it into 4 parts or 4 points, and these 4 steps. Over AI's history, I'm claiming, you have to stand way back and to see it, that experience has played an increasing role in AI, and there are 4 steps. We're going to go through each one of those 4 steps. And in each one of these steps, I'm going to try to make the point that AI has reluctantly moved to be based on experience and be working in terms of experience. It has reluctantly moved into it. It's not our natural tendency, but it brings us concrete advantages. And so we've gradually done that. Incompletely, it's still incomplete. Maybe the first 2 steps are pretty well established. Then second 2 are ongoing. Okay, so I won't foreshadow too much. Let's just get right to it. What's the first step? The first step is agenthood, and by that I just means that our agents have experience, or we've been dealing with agents. An agent is something which interacts with the world, and therefore it will have experience. But for a long time, AI did not involve agents. So in the early AI systems, even before I was in the field, the AI systems were problem solvers. They were given a description of a problem, and they were asked to figure out a solution and then report that solution. They weren't actually asked to do anything. And in fact, they didn't have to sense things because they knew the way the world worked. The world was expressed as a puzzle, including the operators and the actions available in that puzzle. And so they didn't have to, they never had, and the world was deterministic, so they never had to sense anything. So experience was genuinely rare in early AI systems. But then about 1985, which they switched, not totally abruptly, but gradually towards working on agents. And the epiphany was, I like to describe it as coming in the AI textbook, the Russell and Norvig, the first edition of it in 1995, where they explicitly made this point that the unifying theme of the book was the concept of an agent, and the problem of AI is to describe and build agents that have sensations and emit actions. So just if we notice, at the very beginning, in the first 30 years of AI, experience was rare, but now it's the standard modern approach. Now we have this interaction between agent and environment. So this is a case of an increasing role of experience in AI. So that was step 1. Okay, that didn't seem too hard, I hope. We're going to get more challenging. Step 2 is reward, is to have your goals be expressed in experiential terms. This too was unusual originally, but now it's sort of becoming accepted. You used to have goals like to attain a state of the world. Now a goal is perhaps all goals can be expressed in terms of reward. That's what the reward hypothesis suggests. Yeah, let me read that. The reward hypothesis. All of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal called reward. So that's a strong form. That's the other claim is also strong. The reward is enough hypothesis is that intelligence and all of its associated abilities can be understood as subserving the maximization of reward. Today, we think of reward as being the goal. Originally, we thought about attaining a state of the world as being the goal. That's really quick. But so at the same time that I'm claiming it's accepted, I want you to notice that we're still not we're uneasy with it because it's such a strong statement that everything can be reduced to a single number. It just sort of seems too small well, it seemed too small for me. It seemed too small for all of us from when we first think about it. It doesn't seem enough for people just to have this single number from outside the mind. It seemed too reductive, and our goals seem grander, like saving the planet or contributing to human well-being and make the world a better place. But the claim of understanding, the claim of goals being reward is that really it does come down to a single number, and it's something we receive from the world. It's something like comfort or pain, pleasure, hedonism. So this is why we're uneasy with it. To think of ourselves as hedonists is just being selfishly interested in our number. But yet we are driven to it because we need to be clear, and we need to have a clear goal. And if we're going to have things work towards a goal, they have to be plain to them. And I guess there's a little bit outside. Maybe the order is a little funny here. Here's some examples of how AI has been uneasy with reward, but has come to accept it. Like the modern, that AI textbook, Russell and Norvig, it's all about states of the world as being the goal. But as they go through, they end up doing reinforcement learning and reward. And markov decision processes, which use reward, are now the standard way of formulating planning in AI. And even those who don't really like reinforcement learning, like Jan LeCun, have to admit that they still have reward as the cherry on top of the cake of intelligence. So that's reward. I think we are gradually accepting that our goals should not be expressed in terms of the world, but should be expressed in terms of parts of experience, a single number we receive from the world. Okay, step 3. Oh no, I'm not going to do step 3. I'm going to give you an interlude. We're going to step aside and try to think, what would it mean to think about experience? So let's look at some examples. What would experience be like? What would it feel like to be an agent just dealing with numbers and bits? Okay, so here's some experience, a time series. This is a concrete, non-specific example. So it's concrete because I have, things like time steps 1, 2, 3, 4, 5 through 7, and the latest things are here at the bottom. There are 3 action bits, and there are some sensory bits, a whole mess of sensory bits, maybe 10 of them. And they're not just bits, actually. Some of these have values between zeros and ones. The first 4 are zeros and ones, and the next ones take on 4 values. Okay, so this is a small world. There's only 3 bits of action, and there's only 10 sensory signals that are bits or 4-valued quantities. We also have a final signal, which is the reward. The reward is a numerical quantity, which could be positive or negative, and it's continuous. Of course, now the agent is really only dealing maybe with the most recent things, and the rest it has maybe a memory of. And you should think of the time step as being fast. It's like maybe a 1/10 of a second. Okay, so this is happening fast, and you can see the latest one, and you have to make sense out of this as you go on. Okay, now let's kind of color it up so that we can, so it's easier to think about, because this just looks like numbers and bits and it's kind of hard. It will be hard in the end, but we can make it a little bit simpler for our minds, we're all kind of very visual animals. So here I've just colored the signals. So the numbers or the actions are binary. They're zeros and ones, and I'm just going to color them gray for zeros and white for ones. And the sensory signals will do the same for the bits, zeros and ones. And for the 1 of 4 numbers, I'll use 4 different colors. So here the zeros are reds, and the 2s are blue. Of course, the fact that they're 2s doesn't matter at all. They're just signals, 1 of 4 signals. And then the numerical signal, the reward, I'll use a bar graph. So the bigger the absolute value of the signal, I will use a bigger bar. So here's a near zero signal. And I'll use the color to indicate whether it's positive or negative. Positive things are in green, negative things are in pink. Okay, so now you understand the coding, and you can see really that the color coding is almost more informative. So I'm going to take away the numerical part. Okay, so here, now it looks simpler. And this is the problem that our minds are faced with, which is to understand these signals. And what does it mean to understand the signals? Well, the only thing that matters is the relationship between the signals. And so we want to find patterns in these time series. Okay, so can you see any patterns? And I really want you to, I won't stop and ask you to raise your hand, but look at the experience here, and I want you to genuinely look for patterns and tell me, do you see any patterns? Do you see any relationship? This is what the mind has to do. Find patterns. Come to be able to predict and control. Okay, so there are patterns here. Here's one. You notice that the signal, if it's white, on one time, they're slightly offset because right, you get a sensory signal, you take an action, you get a new sensory signal. So anyway, I'm noticing here that if this is white, then the next thing is white. The next value of the first, I'm going to call it a sensory bit. The first sensory bit is white. And if the last action is gray, then the next value of that first sensory bit is also gray. And this holds throughout the sequence. So really, that means that apparently this component, this action signal, causes the next sensory bit to match it. Okay, so that's an important pattern if you're an agent that you can make. If you want to control your sensory bits, this is how you can do it, by sending your actions out. Okay, now here's another pattern that maybe it's a real pattern, is that whenever in this fifth sensory signal is red, then on the next time step, the sixth sensory bit is green. Okay, anyway, we see that happens twice here. We don't know, it could just be by chance, right? Like there's maybe a few chances in 4 that this could happen, and with all these signals, there's bound to be some patterns here, some which are real, some which are not real. So we need more data, and so let's get more data. So here I'm going to show you a bunch more data. And at this point, you're probably wondering, where this data came from. And the answer is the data came from a program that I wrote. And it's made up. The relationship is made up. There's no underlying system who we might explain or understand in world terms. It is just experience, experiential data. This is the problem of the mind, is to deal with experiential data and to make up the story about the world as a way of explaining its data. Okay, so anyway, here we have a bunch of data out to 73 time steps now, and the patterns we've already talked about is these two, and there are more instances of that, and it does hold up throughout the data. Whenever there's a red in the fifth sensation, then the next time step, the sixth sensation is green. So that holds up. And here's another one. After that, 2 time steps later, we have blue. See here? And that holds throughout the data sequence. So I'm trying to show you some examples of patterns in the data and qualitative relationships amongst the data. So let's go through these. Different sensory signals can be qualitatively different. So these first 4 are just bits. The next 4 are 1 of 4. Or the next 6 are 1 of 4 signals. Is it 6? The next 7. Actually 11. There's 11 sensory signals. And the last sensory signal is the reward, is also qualitatively different because it has a continuous and a negative and positive relationship. So these relationships are different signals affecting themselves or other signals at later times. These are predictive relationships. There are short-term relationships. There are longer-term relationships. This 2 steps later is the longer-term relationships, but there could be much longer-term relationships that are harder to find. Your predictions don't have to be just of sensory signals. Now, these predictions are sensory signals. Like here, I'm predicting that after this pattern, 2 steps later, this sensory signal will have this value. But that is not necessary. You can have much more abstract statements about the future. And the best example of that is the one that you're already familiar with if you're familiar with reinforcement learning, which is the value function. The value function is a prediction of the sum of future rewards. So let's go through that. What is a value function? A value function is a prediction of the discounted sum of future reward. So that quantity, the discounted sum of future reward, is called the return. The return is not part of your sensory signal. It is something that takes a value at each point in time. The return is the sum of the future reward, something that you won't know until later. Okay, so let me go through that. Here is the return at a particular time shown by this big green bar. And the fact that there's a big green bar, it means that the rewards that follow this, here are the rewards, tend to be positive. And they're weighted, they're summed up and they're weighted according to their recency. So this gray represents the weighting. We give a high weighting to this first one, which is a big green bar. And then we have several green bars here, and they're highly weighted. We have a pink bar, which is negative. And so that's going to work, to make this return smaller, which is the sum of these bars weighted by their recency. But these mostly large ones make this for a large bar. Now, if we look for a place where we have a large pink bar like this one, I think we slide down there, and for each instance, let's do this. This instance, we have a pink bar because there's mostly pink that follows this time step. And we slide down to another example. Here's some big green bars, and here's that big pink bar, which says that there are lots of pink following it. So that's just, I'm trying to explain what the return is. The return is this number about the future. You don't see it at the time, but it's a well-defined quantity of the future. And you could try to estimate that quantity in advance. Okay. And that would be predicting the return. And that would be predicting a quantity that's not a simple value of what will happen in the future. It's not saying this particular thing will happen in the future, but it'll say this function of the future will have this value. Okay, so this is an abstraction, and we need to get increasingly abstract in order to make a model, make an understanding of our data stream. Okay, and that's what our goal is. Our goal is to understand, predict, and control our data stream. And these are the most important things that we have to predict are functions like the return. And in fact, we've generalized the notion of return to a general value function, which lets us predict things that are not just reward, but any signal, and in a very flexible way, with a flexible temporal envelope. It doesn't have to be just exponential, and it could be contingent on a policy. And these is a major part of the machinery for trying to understand experience, general value functions, predictions. Okay, that was our interlude to start to understand experience. Now, and I hope you're seeing, I like that example that we just went through because it is both abstract and concrete. It's abstract, and the things we're learning about the world are abstractions, functions of the future, and yet it's all very concrete because I'm bringing it down to these bits and four valued signals, and a small number of them, and we can see what the relationships are. Now we have to see that life and intelligence is all that on steroids, scaled up. Okay. Next step, experiential state, to think about the state of the world in terms of experience. And again, the conventional thing is not to do that. The conventional classical AI thing is to represent the state of the world as in terms of the world terms, like, the positions of the blocks, or whether or not it's cloudy outside, or whether or not it's raining outside. Graphical models all work in these external world terms. You have these objective state representations. And that's the classical way. And today, we're starting to see cases where we're doing it experientially. We define the state of the world as well, like I had recently seen some things would be an experiential description. But in general, let me cut to the general case. An experiential state is some summary of the past that's useful for predicting and controlling the future. Like, you might need to remember that you just saw something so that it enables you to predict something about the future. So this description, experiential state, has no mention of external entities. It's just totally experiential. It's not objective. It's not external. And this is starting to become more common. Like most in Atari, we'll take like the last 4 video frames and we say that's the state. Okay, and maybe the last action. So that is experiential. It's not describing the external world. It's describing the experience that led up to a time. If people who talk about compression approaches to AI, they're just saying, oh, there's some bits and you want to compress those bits and predict the future bits. That's experiential state. LSTMs in deep learning, and predictive state representations in machine learning, spectral methods, these things are of this form. And these methods, they learn and discover their state. They figure out what it is they need to remember in order to predict the future. And that's, of course, the essential part of it. State has to be discovered. Now, if you think about the state, here we are, time is progressing down like in this diagram. So this is the most recent sensation, and these are previous sensations, and these are actions. So these two are arriving, sensations and actions alternately arriving. And the state at any particular time is a function of the preceding bits of experience. So I'm saying all these preceding bits contribute to this state. And all that's true because the state is a summary of the past that's useful for predicting and controlling the future. And this question mark denotes that the essential problem of the agent is to look at the current state and generate the next action. That is the agent's task. So get some summary of the past. That's good for generating the next action. Maybe that's also good for predicting the future in the ways that we've talked about. So although this is true, it's not really the way you want to structure it. It should be structured recursively, because if you go, there's a state at every time step. So if you wrote all those down, you'd have all these connections and all these crossing wires, and those crossing wires suggest that this is actually a complicated and not very good way to structure it. A better would be to do it recursively. So you do it recursively. The current state would be a function of the most recent sensation and action and the last state. And you don't have to look at all the old things because they're all bundled up and into this state. Okay, so this is the structure we want. Sort of recursive updating of the state from the most recent sensation and action. And now I want to show you what that looks like as a box diagram. It looks like this. So we have the sensation comes in along with the most recent action, and this produces the next state. And that state also feeds back into the process that's generating the states. And you'll notice that the process that's generating the states I'm calling perception. I think that's a really good name for it. It's always generating a sense of where we are now, and we're going to use that to make our choices. So where we are now, that's the job of perception. And then that state is used to generate our actions, and that's the policy. And it's also used to generate predictions. Well, I got this diagram up here. Let me show you the full picture. Full picture, which has all four of the things that we're going to talk about. For example, sensation and action, agenthood, and reward. Reward just comes in as a special scalar that goes into the value function. It's or many value functions into our set of predictions. The value functions, of course, are used to change the policy, and the policy is also changed as having a model. The model changes the policy through planning. Okay, so this is the ultimate diagram that I get to in the Alberta plan, and if you want to read more about that, you check out the Alberta plan. But we'll want to go further and do the last step. The last step is knowledge, predictive knowledge. That's really this part. The model of the world is going to be our knowledge, because we're going to predict the transitions that the world might go through. Okay, so and now the gulf between common sense notions of knowledge and the experiential notion of knowledge is large. So we have to acknowledge this gulf. Joe Biden is no longer president, but so these are common sense notions of knowledge. Birds have wings. The car is a few meters ahead of me. These are largely like the location of the Eiffel Tower is not experiential. It seems like it's just talking about the external world. That's our normal way of talking about world knowledge. Now, but other things are seem more experiential. So I've written down a bunch of things that seem more experiential. It's a long walk to the city center. I can deadlift so many pounds. It's cold. My foot is sore. The seventh pixel will be blue in 3 steps. Right? That's very experiential. But there's a big gap between the common sense knowledge and experiential knowledge. Maybe fire engines are red. It's getting a little bit experiential. There's this gap that has to be crossed, and that is the challenge. And yet it seems impossible, but maybe it seems impossible in the same way that it seemed impossible that reward could express all of our goals. We just have to use imagination and some abstract thinking and maybe we can reduce things. And maybe in the world of large language models, where we have symbolic knowledge being expressed by things that just see bits, maybe this seems a little bit plausible, or maybe it doesn't. Anyway, I think it's quite challenging and important. And yeah, we're going to reluctantly do it. So I don't want to use up all my time, so I'm going to go a little bit fast. But it's the same story, really, is that the early AI is all expressed knowledge in terms of like probability relationships between states of the world. They would never talk about experience. They would talk about truth, and they would talk about simultaneous events, not even in general, typically sequential events where you would have prediction. Because there was no, remember, in those early AI systems, there was no experience to be talked about. But nowadays, it's quite common to talk about a predictive model of the world as the view of AI knowledge or world knowledge. And I think the cutting edge of this is the idea of general value functions. And a related idea that's called option models. Option models let you express large-scale temporal relationships that don't have to be one step. So let me talk a little bit more about this. Distinguish between mathematical knowledge and world knowledge. So mathematical knowledge, 1 + 1 is 2. How large is pi? This theorem is true. This is true. The sense of truth in math is not about this world, because it will be true in any world. It's not a true fact, empirical fact about the system that we are interacting with, our world. They are absolute truths that are timeless and universal. And so in this sense, it should be clear that they're not knowledge about our world. They're not about the world. Knowledge of the world, generally about the world, is of two types. What state am I in, and what is going to happen in the future. Predictive knowledge. We've already talked about state. Now we have to talk about state transitions, predictive model of the world. And I want to say that this model doesn't have to be low level. It doesn't have to be, okay, I see this on this state, so I tell you what the next state is going to be. It can be, I think that's a go-to default thought, that the model of the world would be like the transition probabilities of a Markov decision process, or that the model of the world would be a set of differential equations. But instead, it can be quite abstract. It can be abstract in state, it can be abstract in time. We've seen how it can be abstract in state by having experiential state. And you can also be abstract in time. Your predictions can be dependent upon whole ways of behaving. Like you might have a prediction, like if I go to the talk, I might see my friend Amir. Or you might have a belief that if I go downstairs, I can make tea and I'll feel warm liquid in my mouth. You might say, if I take this job, that I'll have a happy life. Okay, so this is knowledge that's experiential, but it's not single step transition. It's about over the long period. So there's a well-developed theory of how we can express and learn temporally abstract knowledge, and it's based on the idea of an option. Option is meant to be a similar word to the word action, and so it's a choice that we make, an option, but it doesn't last only one time step. It's a whole way of behaving, a policy, and a way of stopping. And your model of an option would be your model of, if I behave this way and stop the way it says to stop, then at the end of it, I expect to be in a new state that has some properties. Okay, so that would be a transition model. So it's quite expressive, and it's not clear what the limits are. Maybe it'll be sufficient to capture all experiential knowledge, to have option models and experiential state, and they may enable us to bridge the abstraction gap between, Joe Biden being president and the seventh pixel. The one-step trap is to think that you can do just one-step predictions and that's enough. Many of you may be thinking that. It's true that if you could do them exactly correct, it would be fine. But you can't get them exactly correct. There's always little errors, and the iteration amplifies it. And so in the long run, it just doesn't work to model the world only at the micro level. You need to model it at the higher level. Not widely understood, universally understood. There are so many people that are stuck thinking they can model the world at the single time step level. But it clearly can't be done. Is it a good starting place? Not if you get stuck in it. So many of our methods are stuck in it and they rely on it. Okay. That's just a few general comments. Experience is fundamental to world knowledge. By definition, we gain information about the world only through our sensors, and we affect it only through our actions. So the only way we know the world is through our experience. And so it follows that everything you know about the world is a fact about your experience, a statistical, empirical fact about your experience. You may not think about it that way. You may think, oh, I'm taking a sip of water from my mug. But really, that's a belief about some complicated sequence of actions and motor actions and the sensory outcomes. It's a complicated fact. This perspective seems inescapable to me. In the long run, it's a good thing, the fact that we can, our knowledge is expressible in terms of experience means that you can verify it and learn it from experience. But we don't like to think in those terms. We like to think about, the coffee mug and going to the kitchen and taking the job. So, I think it's important to recognize why we dislike experience and then why we have to do it. We dislike it because it's unfamiliar. It's all these little tiny bits, like in the example. It's temporal. It's complicated. It's sort of intuitive. It's just so low level. It's hard to talk about it. It's private. My experience is different from your experience. When my red pixels light up, it's not your red pixels. We can't talk about it. It's nothing that we share. Really, for almost everything that we do, it's superior to talk in terms of objective terms. External objective terms are superior, but the exception might be, for making AI. For making AI, we have to talk about experience. Okay. Now, why is it really good, potentially really good? And that's that experience is available. It comes from the ordinary operation of AI. It's free data. If I have an agent interacting with this world, it's getting experience. And so we could learn from that experience and learn autonomously and scale. If we have bigger computers, we can find better patterns in our data. It scales with computational power. So an experience offers this path to know the world. Any fact about the world is a fact about experience. So it can be learned and verified from experience. This is not true. Our large language models, they have no way of verifying. They're just summarizing what other people have said. Is it true? Is it wrong? Does it have a clear meaning? No, it doesn't have a clear meaning. Only from actual experience can you get that clear meaning. So if we can learn and plan from experience, then the whole agent becomes grounded and scalable. This is the vision. This could be super powerful. And it's a necessary step, I think, for AI to succeed. Okay, in summary, I've discussed 4 major steps in the increasing role of sensorimotor experience in AI. Agenthood, having experience, reward, goals in terms of experience, experiential state, having our state of the world expressed in terms of experience, and predictive knowledge. To know the world is to predict your experience. For each one of these steps, I've shown that AI has chosen to work first in objective, non-experiential terms because that seemed natural, but that there is a less familiar approach based on experience, which is growing in importance and its advantages. It's grounded, its learnability, and its ability to scale. Now, I think the trend toward experience in AI has much farther to go. The second steps 3 and 4, they're far from complete. There are lots of great research opportunities to work on them. You have to think more abstractly. And ultimately, I think the story of intelligence may be told in terms of sensorimotor experience. So, yeah, if I want to express this idea in one slide, one slogan, I would say this: data drives AI, and experience is the ultimate data. It's the data that we will always have. We'll have in infinite quantities, and we'll have it from just normal experience. So I want to take your questions, as I'm sort of done, but I want to prime you a little bit and put on the table some obvious questions that you may hesitate to ask. So let me, well, first, thank you for your attention. Mention some of the many people who have helped me in the whole team in Alberta. This isn't even the whole team. We have a large team, 10 professors and many hundreds of students or so. Let's prime you with a few questions, maybe objections. Okay, so here's 3. First question: not everything is learned from experience. Some things are built in. Yes, some things are built in, but this is not relevant. My point is not that everything is learned from experience, but it's really more that everything is about experience. The content of the knowledge is grounded and takes meaning from experience. So even if you have built in that this motion will cause this result, or even if you have built in that if you see something with like a snake, it might be dangerous. Lots of things are built in, that makes sense, but their meaning is experiential. That's the key thing. Second question: surely people can build in important abstractions, which would save the agent a lot of time. Maybe we can add the links to experience later. And this is also true because you can build in important abstractions, but then you haven't really understood the process of discovering them. If you build things in, you're just kind of cheating, and it makes you harder to see how the agent can do it. So this is what I mean when I say this has been tried, but it has never been done successfully at scale. And this is really the point that the bitter lesson tries to make, that building how you think you work is a strategy that is ultimately unsatisfying. It's satisfying in the short term, but it fails and is beaten out by things that are scale better because they're more general. Okay, and at the same time, it is possible that you can build in stuff after you have the experiential abstractions. You have the notion of a coffee cup, and you might have the notion of water, and you might be able to combine them. And the final objection is that just that this gap is so big. This gap between experience and knowledge is so big. Maybe we can't do it. And that just means we need to be ambitious. Computer power is big. Human ingenuity is big. We should be ambitious. We can cross this gap. We must cross this gap. We can see gaps being crossed. We've seen AI done amazing things in large language models. We've seen AI do amazing thing in AlphaGo and its descendants. We can cross big gaps with computer power and human ingenuity. Thank you very much for your attention. And now I'd be very happy to take more questions from you folks for pretty much as long as you have patience.